whatever I could do to figure out how on earth that was, how on earth that worked. Like, what were our regressions really doing? That's where this paper came from, and it lingered on my computer as notes for a long time, and I did it wrong many times, and I like wrote out all these pages of the algebra. I was forgetting something or doing it wrong, and it only sort of started to congeal into a real paper in about 2015 or 16. And so there we go. So that's what I'm going to present to you today. And I'll try to go get to the main part as quick as I can. So we can talk about like what you learn from the main result. I view the paper as having like this one result about like describing what the two-way fixed effects differential coefficient really is. And then you can take that result, you can learn a lot of other things from it. So I'm not going to linger on this, but I think this is sort of an amazing thing to say, especially today, because literally there's like wastewater testing for COVID in Southwark and Lambeth, which are areas of London. Like today they're doing it, but that's the genesis of diff is like waterborne illnesses in London in 1850s cholera epidemic. So of course, like John Snow, this epidemiologist, was comparing death rates between two epidemics, two cholera epidemics in the 1850s. This is a period of time where like people didn't know that cholera was waterborne. The working hypothesis for most disease was that it was caused by miasma or just bad air. So there's like two epidemics that just would come in waves in London because homes were being supplied with water straight from the Thames River, which was also the discharge site for sewage in London. And so, you know, you have these earlier epidemics in this pre-period, 1848, and houses served by these two companies, Lambeth and Southwark and Vauxhall, had very high death rates. That's what you see here. They both had quite a few people served by both companies died when there was a cholera outbreak. And then the Lambeth company moved its intake source upriver, so it was drawing much less sewage when it provided drinking water to homes. And you see that in the 1850s outbreak, their death rate went way down and the control groups didn't. So, I mean, this is the genesis of diff and diff, which I'm sure you heard before, but I just like showing it in this table where we can now give our current notation to this 1850s era table. You know, so you have the Lambeth company is the treatment group. They start off untreated with clean water in the sense that they have disgusting water. And then they move their intake site and they are treated with cleaner water. And the control group are homes served by the Southwark and Vauxhall company, and they have dirty water all the time. They're never treated with clean water. And so, you know, the basic logic is if you were to just compare death rates, say in the post period, right, in the 1850s, you'd say, oh, fewer people die in the Lambeth company households than Southwark and Vauxhall households. But how do you know? That's not because Lambeth company has more expensive pipes and rich people put them in their homes and they do other healthy things. Or how do you know that the companies aren't serving different areas of London? All these things. And so the logic of diff and diff is to say, well, if those differences are the same, let's just look at how those two groups of households fared in an earlier wave and subtract that off. So you can get the change in deaths in the treatment group before and after they actually get clean water, the change in deaths in the control group, and you know, you get a typical, what I'm calling 2x2 diff and diff estimate. So 2 means two groups, by 2 means two periods. So treatment control and pre-post, that's 2x2 diff and diff. And it's these four numbers, and this is great. Like this is what we've known about diff and diff since the 1850s. And it's really good. It's like a really great idea because it's so simple. You just need four means. You know, -10 is the diff and diff estimate. And we just have to eyeball that. That's easy with just these four numbers. The other nice thing about 2x2 diff and diff that economists and social scientists have used for a long time, since at least some papers by Ashenfelter and Card, I think in the late 80s, but more explicitly since Card and Kruger's minimum wage study in 1994, I think, is that you can get this same, I'm going to skip the picture version because we'll look at these pictures a lot later. The real flexible thing about 2x2 diff and diff is that doing it by hand, which is nice and intuitive and clear, and you don't need to show anybody anything complicated, is that it gives you literally the exact same number that you get when you run a regression of outcomes. So like death rates, for example, on a dummy for the treatment group, a dummy for the post period, and an interaction of treat times post. So beta hat diff and diff from this regression is algebraically identical to beta hat diff and diff that you calculate by taking the average outcome for the treatment group in the post period, subtracting off the average outcome for the treatment group in the pre, and then further subtracting off that same difference for the control. So why is that Why is that like a key step for the spread and the dissemination of diff and diff? Well, basically because regressions are easy and flexible. They're quick to do. They're canned. They give you standard errors really easily. I mean, they're just really convenient. And this is like noted in mostly harmless econometrics, for example, you can add controls to them. You can add different kinds of treatment variables to them. You know, what if your treatment is continuous? You can use the regression tool to extend the underlying logic of diff and diff in a lot of different ways. And so that's basically what my paper is about, is when you extend that to a different case, in particular, the case where treatment doesn't just turn on at one time. It's not just that we're comparing 1853 outbreak to 1848 outbreak. It's that different units, states, counties, firms, workers, whatever, different units in the data set, they might get treated at 1 year, another group of units get treated in a different year, and another group of units gets treated in another year. That's staggered timing. That's variation in treatment timing. For me, one of the primary examples that comes to mind for this kind of thing are studies also from the early 90s about worker displacement. You know, asking what happens to workers' wages after they lose their job, say in like a mass layoff event. So Jacobson, Lalonde, and Sullivan have really nice papers where, you know, you look at workers who are fired from some plant in Allentown in 1991, and you want to compare their wages to other workers who are fired from someplace in Youngstown, Ohio in June 1993 or something like that. So workers aren't getting fired at the exact same time. It's happening differently. And we naturally want to exploit that somehow. And using a regression is the way that we've typically exploited it. So that sentence right there, like how are we exploiting it is what I'll say a lot more about now. So, you know, variation in timing looks basically like this. This is the picture that most simply can show you what variation in treatment timing looks like. One group of units, here I've got them called K, they are trucking along, and here at time T star K, they jump up and they get treated, right? So they get hit with a treatment right here. And the way I've drawn this, their outcomes shift up permanently and forever, and then they just keep on going. There's might be another group of units. Here I've called them L, and they get treated later. So here at T star L, they get hit with the treatment and they jump up. And here I've drawn it so that they jump up by different amounts. And then maybe if you're lucky, you have a whole other group of units. You know, for me, this was the 2,900 counties that never got a health center. This might be thousands of workers in your administrative data set who never get laid off. This might be states that never expand Medicaid under the ACA. You know, lots of groups that never do something. They're just this gray line, and they're just moving along like normal. My question was like, what does the regression do in this case? And I'm going to skip examples because I've just given a bunch of them. But the way that economists have dealt with a situation like that, you know, I think the thought process is something like, well, if we had less data, we could do a simple diff and diff, right? If we just had data on the early treated group and the untreated group, we would be in Card and Kruger world. We'd be in simple diff and diff world, and it would be obvious what to do. But we've got this other unit, like, I don't know, what should we do? And the answer has typically been to generalize that regression equation. And people think, and it's like, this is good, right? Like we say, we want to run a regression, and normally we had a dummy for the treatment group, but actually look at this. Instead, we'll put in a unit fixed effect. We'll put in a different dummy for every single unit. And like, that's gotta be better, right? That's way more flexible. And they said, oh, well, we used to have a dummy for post, but now post is something different for the early treated group and the late treated group. And so there's not such a thing as one definition of post anymore. But look at this, we can be more flexible, and we can put in time fixed effects, like dummies for every single time period. Again, the regression logic says, isn't this better? This is way better. This is more flexible, you know, more dummies, more flexibility. And then the other thing you stick in the regression is just a treatment dummy. DIT equals 1 if unit I has the treatment at time T. So, you know, like there's 20 some states that expanded Medicaid in 2014. So those states would have this dummy equal to 1 in 2014, 15, 16, 17, 18, et cetera. But then there's some states that did it in 2016. And so they would have it turn on later. And what we've typically done is, first of all, run this regression thousands and thousands of times. This is really the go-to way to handle treatments that vary over time, that turn on at different times, is to run this kind of regression. And then we've gone on and imported a lot of the logic and a lot of the interpretation from 2x2 diffindiff and basically applied it to this kind of case. We've sort of, I think, made a little bit of imprecise arguments about, what we need to assume for this to be a good idea. Like we've kind of fudged our way through what parallel trends means in this case a little bit. We've said, oh yeah, in when you run a 2x2 diffindiff, under some assumptions, it's going to estimate a parameter that's called like the average treatment effect on the treated. And we say, yeah, this is like that. This is probably going to give us an ATT, et cetera. We've taken a lot of the 2x2 logic and imported it here. And basically what my paper shows is that that's not true. And that's not really how this estimator works. And you can learn a lot about the pitfalls of this strategy by digging into it. So the central result of the paper that everything else stems from is literally just taking this coefficient, beta hat diffindiff, from this equation and breaking it apart and saying, like, what is it? Where does it come from? What kinds of comparisons in the data actually give rise to that number? And the thing I should note, if you're all like digging into some of the new literature on this, is that this approach of starting with the estimator and doing algebra on the regression coefficient first is different than a lot of the other papers do it. So Deschaise-Martin and Dafoe, Anton Stresnev's paper, Borusiak and Jaravel, like these other papers also show some version of some of the things that I show, but they take a more traditional econometrics approach, and they move right to the theoretical interpretation of this coefficient. They're saying, like, they're writing it as a function of treatment effect parameters and talking about, like, how do we interpret it? I'm breaking apart the coefficient itself. So everything you're going to see in the next few slides is going to be functions of like Y bars, right? Like sample quantities, things you can actually calculate. And then I'll use those to understand the theoretical interpretation. These other papers are going right to the theoretical interpretation. And in we're all coming to the same conclusion on some things, but there's other things that I can speak to because of this slightly different approach. So let's look at this. Let's look at how I'm going to start, right? I'm not going to sit here and walk you through all the algebra, but I'll show you like where it came from. The algebra of the Frischwald-Lavelle theorem is just that when you want to know what beta hat diffindiff is, the coefficient on one variable, and your regression has a bunch of other variables on the right-hand side, you just have to partial those out of D, the variable you care about. And when they're fixed, and when they're X's, it's really annoying, but when they're fixed effects, you could do it with means. So what Frischwald-Lavelle tells us, or what Frischwald tells us, is that if you want to know what beta hat diffindiff is, all you really need to do, in fact, you don't even need to do this Y step, actually. All you need to do is take out unit fixed effects. So you see D bar I, that's the average of D for unit I. Like just average that dummy across all the time periods for Alabama, or for one firm in Youngstown, or for, Washtenaw County, Michigan, or something like that. And that's D bar. D bar T is the average of the treatment dummy in one time period, in 1 year. And Frischwald says, you just have to take out the means, the unit means and the time means, subtract them from D bar. And that's what this first expression is. And then you've got this thing called D tilde. And now this is what got me in a position to actually do all this algebra, was to be able to express beta hat diffindiff as a univariate regression coefficient. That's just a covariance over a variance. And I know how to manipulate covariances. It's much easier than manipulating whole matrix regression coefficient formula. And so that's how I started. Like, I just got this expression down here at the bottom. Beta hat diffindiff is a covariance between this fixed effects adjusted version of D, and it equals something like this. And I just did algebra on it, and I'm going to tell you the answer rather than go through it, because it's a little painstaking, but it does give you a nice intuitive, at least I think, answer for where does the regression coefficient come from as a function of like sample quantities that are easier for me to understand, at least. So I'm going to go back to the picture to tell you like where it comes from. So I said, oh, well, if we just had less information, this would be so much easier. So I think I usually try to motivate the interpretation of this big finding in terms of thinking about this picture and saying, well, what are all the simple things we could pull out of it? Like, what if we just forgot about some information? So imagine that you didn't have that late treatment group at all. Well, then you would be comparing the early group, K, they switch right here. They enter treatment right here at T star K. And you'd be comparing them to the untreated group, people that never get the treatment. And that's easy. Like this is a diff and diff that we've known how to do. This is a 2x2 diff and diff, and we've known about it since 1850s. And we could just calculate it, right? It's just going to be the average of these black triangles after T star K minus the average of the black triangles before T star K. That's one difference. Minus the average of the gray line after T star K minus the average of the gray line before T star K. That's the second difference. So that's one. So if we had less information, we would know what to do here. But you could also say, well, what if we didn't have information on the early treated group? Well, you could do the same thing, but now the treatment group in this simple 2x2 diff and diff is the late treated group, L. And again, the control group though is the untreated guys, YU. So this is another, now we've got two simple 2x2 diff and diffs that we can get. We can compare early to untreated, or we can compare late to untreated. And those are two different estimates. But there's actually two more estimates, which is that there's two different ways we could now compare the early to the late guys. So suppose these are the only two units we have, like somebody switches early and somebody else switches late. A friend of mine, Olga Malkova, who's at the University of Kentucky, has a paper like this. Like there was a maternity leave policy in Russia in the 80s that hit half of Russia in like 1981. And then it just hit the other half of Russia a year and a half later. That's it. That's the whole variation. So sometimes this is literally what you have. And there's two ways you could make the comparison here. What if we just didn't have data after T star L? Like what if the data set didn't even extend that far? Well, then we're back in simple diff and diff land. We can compare the change in outcomes before and after T star K for the K group, like the early group. That's one change. And as a control group, we can use Y star L because they're not treated yet. Their treatment dummy is 0 this whole time, all the way here. Before T star L, they can be a control. So this is yet another simple 2x2 diff and diff. But the real tricky one that was not intuitive to me until I really cranked through a lot of this. And actually, this next thing is really where the problems with two-way fixed effects arise, is that technically you could also do this. And this is and the regression does do this, which is you could, in principle, compare the change in outcomes before and after T star L for the late switchers. So they're going to go from 0 to 1. And as a control group, you could use the early switchers. Now they're treated, right? But their treatment status isn't changing. It's constant at 1. And so the way I've drawn this is the way that it works really well, which is that those early treated guys, they're treated, but their outcomes are changing only because counterfactual outcomes are changing. Basically, like the treatment effect's not changing at all. It's just a big shift, and then everything else is as it was. That's really important. And so what I want to tell you here is that this is like another comparison that you could make. And you could form a 2x2 diff and diff by doing this comparison. Use the late group as the treatment group, late switchers as the treatment group, and use earlier switchers as the control group, but only after they're already treated. And so the result in my paper basically says, in a situation like this, the diff and diff coefficient from two-way fixed effects, beta hat diff and diff, is a weighted average of those four things. Okay, so the betas are these pictures we just looked at, right? So this first one, beta hat diff and diff, K versus U, that's the first one we saw. Group, the early switchers are treatment, untreated units are the control. The second one is beta hat diff and diff, LU, that's the one we saw second. The late treated units are the treatment group, and the untreated units are the control group. The notation here is, I want to say it out loud so that it's clear when we look at it later. Beta hat diff and diff, KL, right? KL is telling you which two groups are being compared, K versus L. Those are the early versus late. And then up here, the K up there sitting in the superscript is telling you this is the one where group K is the treatment group. That's the early switchers. Okay, so that's right here. That's the early group versus late group before T star L. And then this last beta is the flip side. We're going to compare K versus L, early versus late. But now we're going to use the late guys as the treatment group and the early guys as the control. So these are the components that give rise to beta hat diff and diff when you run two-way fixed effects. And I said they were a weighted average. The weights are these S's right here. And I've really come to have an affinity for these weights because they're just so classically OLS. Like every feature of these weights is just what regressions do all the time. the first thing the first component of each weight here is a sample size thing. So when you see little n's, what that means in my notation is just what share of units are in this group. So little nk is what share of all the units are in treatment group K. That would be like what share of all the states expanded Medicaid in 2014. What share of counties established a community health center in 1966, something like that. And so this is telling you, like, when we compare group K and group U, the share of units that we're using is NK plus NU, and that's going to get squared because OLS likes big units or big subgroups like a lot. And when we look at the timing comparisons, this is just telling us what share of units do we use. Well, we compare group K and group L, NK and L, right? That's the total share of the units that we use. But don't forget, when you compare the early to the late switcher, you're not using all the time periods. Okay, you're cutting off some of the data after group L is treated. You actually only use 1 minus D bar L of the time periods. Here, what D bar L means is this is the share of time periods that late units spend treated. So this expression inside the square is the share of observations in your data set that are getting used to calculate this particular 2x2 coefficient. And then the same thing down here, you're just using a different share. So the first part of the weights is sample size. Like if your group is bigger, then terms involving that group get more weight. The second part is the one that's that I just have come to recognize as just like classic OLS. It's the variance of treatment. And what does that mean? Well, I told you that we're going to build up this regression coefficient from like subgroup estimates, and OLS is going to give more weight to subgroups where the treatment dummy, the fixed effects adjusted treatment dummy, varies more. And there's two reasons it could vary. These terms right here, NKU times 1 minus NKU, or NKL times 1 minus NKL, or whatever, that's just telling you how big is the treatment and control group in that pair? How big are they relative to each other? How concentrated is it? If there's just like one unit that switches at time K, time T star K, and it's being compared to a giant control group, that's not a lot of variance because only one unit is really getting treated there. So this is telling you like this is going to be big. That first part is going to be big when the treatment and the control group are equally sized. The second part, and that's true across all of them, the second part, and actually these D bar terms that are coming in this second part of the weight, they look different across these three lines, but they're actually the same. They are measuring timing. So imagine the comparisons that are early switcher versus untreated unit, okay? Early versus late. D bar K times 1 minus D bar K, that's just like what share of time is in the pre and times what share of time is in the post. And so if you're treated like right away, the pre period is very, very small and the post period is very, very big. If you're treated almost at the very end of the panel, like T star, cap T minus 1, the post period is minuscule and the pre period is huge. And those are situations where there's just not that much variance. There's not a lot of time that you observe in the post and the pre. One is big and one is tiny. So this is how timing affects the variance too. And these things all matter for the weights. So, think about this very first line. This is telling us what's the weight on the comparison between early treated units and untreated units. Well, the first part of the weight tells us that if either of those groups or both are very big, it will get a lot of weight. Okay, that makes sense. The second one tells us first, if those groups are equally sized, they'll get more weight. But if one is really small compared to the other, it's going to tend to depress the weight that it gets. And the last one says, if that early treated unit switches really close to the middle of the panel, right? Like P times 1 minus P is at its max when P equals 0.5. If it's treated right at the middle, it's going to get the most weight. But if the early treated unit is treated like right at the start, its timing means that it doesn't have very much influence in this regression. And so these are things like the fact that these are treatment variances in these subgroups, that was one of the algebraic facts that took me a long time to really tease out and settle on. But once I got to that point with this paper and with this decomposition result, I was very happy with it because it is how OLS handles heterogeneity all the time. So the only other analogy that I'll give you here is if you go back to like Angrist's papers from 1988, 1990 on two-stage least squares, and the particular, like the Wald IV theorem, the way that a two-stage least squares estimate equals a weighted average of Wald estimates that compare like two values of the instrument. It's just like this. It's almost exactly like this. Values of the instrument that are farther apart, they have more variance and they get more weight. Values of the instrument that are more common, they have more sample size, they get more weight. So in some ways, I think of this just like a Wald IV theorem, but for two-way fixed effects, differential. So that was for the three group example, but the main thing in the paper shows that this is true for any setup really. And so all you need to think about when you look at the more complicated version, it's really not different than what we just saw. Like this version says, these first two terms are comparisons for one treatment group versus untreated units. That's anything with a U in it. And then the second term are all the comparisons that are treated versus treated, like early versus late, late versus early. And that's all the main theorem says. This first sum is every treatment group compared to the untreated groups. That's one kind of 2 by 2. And then the second set of sums is just every way to compare different pairs of timing groups. So in the example that I'll talk about later, you have states enacting divorce reforms in 1969 and 1971 and 1973 and 1974, and you can compare every pair of those dates, and that's what the regression does. And every time it compares a pair of dates, it uses weights that are a function of sample size and subgroup treatment variance, and that's it. So now we've reached like node number 1. Like we've reached the decomposition result, which says, where does the regression coefficient come from? The answer is it comes from a big weighted average of simple diff and diff terms, each of which we understand, each of which we've understood for 170 years. And now we know the weights too, and the weights totally derived from the fact that we used a regression to estimate this thing. And so everything else in the paper follows from this weighted average. And the other thing I just want to cycle back to and emphasize is everything in this expression right here, this is almost not even an econometric expression. Okay, this is just an algebra expression, right? We haven't talked about the statistical properties of anything. There's no error terms. It's not consistent. We're not talking about consistency or unbiasedness for anything. This is just using algebra to break apart the estimator, a regression coefficient, which honestly I find to be like kind of a confusing object most of the time. And we've turned it into a simple thing, which is a weighted average of means and diff and diffs, which is something I understand way better. And this is, for me, this was like the foot in the door to then understand all the theoretical issues that plague two-way fixed effects. Does that make sense to people? Okay. All right. So the first thing I want to talk about is we're not going to pivot to theoretical stuff quite yet, because the very first thing you can do when you know that your regression coefficient, -4, like positive 10.3 or whatever, when you know that it's a weighted average, a bunch of stuff, you can really start to see where does it come from? Like what influences it? What matters for that magnitude, like where does it come from? What parts of your data really drive the answer that you're getting? And so for that, I'm going to pivot to an actual example. And for that, and my example is to replicate this paper by Betsy Stevenson and Justin Wolfers on unilateral divorce. And this is a really good paper. This is published in 2006, I think. And it is an examination of what happens when states switch the legal regime that governs divorces in their states. So for a long time, it was that both for a long time, it was like much more oppressive to women than this. But then at some period of time, to get a divorce, both partners had to consent. And so if one person wanted to end a marriage, but the other person didn't want to, they were basically trapped. And starting in the 60s and 70s, states started switching to what's called unilateral divorce, where just one person can request and obtain a divorce on their own. So what you got to imagine here is that this paper is about what happens to men, but mainly to women, when they're able to leave a marriage that they previously would have basically been trapped in. And they look at a lot of outcomes. The one I'm going to look at is female suicide. And it's a really perfect, just two-way fixed effects state policy rollout example. So this is their estimating equation. This is a QJE paper. They have dummies for whether a state has unilateral divorce. They have state fixed effects. They have year fixed effects, and there's some controls, but we're going to skip the controls for now. And this is their main finding. When they put female suicide rates per million on the left, they get this nice flat looking pre-period when they estimate their event study. And then there's this like downward trend in suicides that starts right after. And this is like exactly what you want when you run a two-way fixed effects. When you run an event study, this is what you're hoping for. So it's like a solid result. And I have to say too, like it was pretty simple for me to replicate it using data that I just had on my computer. So this is way before posting replication files. They didn't share anything. I didn't request them to share anything with me. And I was able to replicate basically the same result from my own data. So you see a flat pre-period, right? This looks good. You see a downward trend in suicides. And the diffident coefficient you get in levels here is about 3 suicides per million women. This is what you get from two-way fixed effects. And so what you can do once you know where the number 3.08 comes from, like when you know what weighted average it is, you can just plot the weighted average. So this is what Bacon decomp will spit out for you. And I think practically speaking these days, you should think of Bacon decomp as kind of like a tool to check things as you're going along doing your papers. Maybe Bacon decomp graphs will show up in published papers, maybe, but I kind of doubt it. I think it's more a tool for checking and understanding what's going on. But what I've done here and what the stata command will do is that this is just a scatter plot of the 2x2 diffs on the y-axis. So the height of each dot is the magnitude of a beta, and the x-axis is the weight. Those are the s's that we looked at. These magnitudes are the sample size times the variance term. And so what you can see is like, well, which terms really matter? Well, okay, so this comparison, this open circle right here, I think this is the comparison between 1973 states and actually a potentially problematic group of states that switched like before the data set even started. So they're getting used as controls, basically. They get like, this comparison alone gets like 12 or 13% of the weight. And then, other ones, this triangle right here, this I think is 73 versus the group of states that actually never implemented this unilateral divorce policy during the data set. And what you see down here in the X's is that all those little timing terms, this is like a really typical thing, this like funnel shape. All those little timing terms, they're so small, right? Like they don't use very much data. They're typically using a shorter they're always using a shorter pre or a shorter post period because they're dropping some time periods, if you recall. They are noisier and they get lower weight. So you can see that as it spreads out into the funnel shape down at the left, all the low weight terms are they're noisier and and it makes sense. So I think this is what we would expect. Like you use less data to get each point, and what do you know? The points are all noisier. But this sort of shows you like which terms are pulling the weight here. We'll return in a little bit to what the subgroup estimates mean, like what happens when you get the average diff and diff effect for one type of comparison versus another type of comparison, right? Like treated versus untreated, or early versus late, or late versus early. And basically the result that we just looked at, the weighted average, says the average of the height of the dots weighted by the x-axis, the average of the y-axis weighted by the x-axis is negative 3.08. Like that's the decomposition result of the paper. So that's what you see here in this red line. So to me, this is helpful. It helps me evaluate whether I think my estimates are really driven by just like one group or one type of comparison, or if if comparisons between timing groups are giving me a way different answer than comparisons between treatment and untreated groups are. Those are all like good diagnostics that I have used in the past to understand what's going on. But I think probably you'll all leapfrog Bacon decomp in everyday use, and soon enough likely just learn more about using like Callaway and Santana, or using alternative estimators that don't deal with don't have any of the problems that now I will tell you about. So, okay, now we'll like make this little jump to theory land. Okay, so we have like decomposition result. And this, I mean, I can remember when I realized that the weighted average result was going to make it like kind of easy to talk about potential outcomes. I never really thought about it that way before. But now it's just an average. It's not a regression coefficient anymore. It's just averages. And it's really easy to plug in potential outcomes notation into weighted averages. That's no big deal. So that's basically what I do in this part. So for now, you need to suspend disbelief a little bit and say, let's just imagine that untreated potential outcomes, okay, Y0, are trending, they're exactly the same between every group. So we are not now going to worry at all about the typical parallel trends assumption that you worry about in diff and diff. Like when you do that 2x2 diff and diff, of course, you're concerned that untreated potential outcomes would have changed differently, even if there had been no treatment. That's the classic like threat to validity, internal validity of a diff and diff design. The scary thing about two-way fixed effects is that now I'm going to tell you what problems it can have, even if that's exactly perfectly true everywhere, always. So we're going to say for now, potential, like untreated potential outcomes are identical. Like it's the best diff and diff design by that criteria anybody's ever seen. It's exactly perfect. Then let's define like what does a treatment effect parameter mean for a given like 2x2. So we're going to define an average treatment effect on the treated for group K. So this would be a treatment group. Like for the group that switches at time K, they have an average treatment effect just for them, just for that group. And inside the parentheses here, W is a time period. Because if you remember, we're going to like get treatment effects not just in one period, but like averaged over a whole post period. So, you know, if I were to show you like ATTK, and then inside the parentheses, it'll say something like post or like post K. That'll be like the average treatment effect on the treated over the window after group K is treated, T star K through cap T, like the end to the rest of the data set. So it's just going to tell you over which little windows are we going to think about treatment effects here. So like I said, let's forget about things in these pictures that are like differences in the U's. Only look at the ATT parts of these pictures. Let's go back to each 2x2 and say, like, what are you estimating here? Like, if we think that the potential outcomes, the untreated potential outcomes are perfectly parallel, what are we going to estimate? Well, for the comparison between group K and group U, we're going to get ATTK post K. It's going to be the average treatment effect of, specifically for this group, averaged over this whole post period. Okay, that's the parameter. That's like the treatment effect parameter you get from that one 2x2. Then let's go to the next piece of the decomposition and say, what's the treatment effect parameter we get from this 2x2? Well, it's for a different group, right? Like the treatment group is different now. It's the late guys instead of the early guys. And the size of the post period is different too. It's not that long early group post period. It's this kind of short late group post period. That's fine. That's just a different treatment effect parameter. It's ATT L post L. So now we know the causal effect that we get from term 1 and term 2. Let's see what causal effect do we get from like term 3, the early versus late comparison. Well, now we're back to having the treatment group be K. Like K is the group, but it's a different window, right? We're not comparing all the way to the end of the data set anymore. When the late guys are the controls, we can really only go up until time T star L. So we're going to get a slightly different parameter here. It's going to estimate ATTK, they're the treatment group, but over the window that I'm calling mid KL, that's just this time period between treatments where the early group is on and the late group is not on yet. So same treatment group, but just different time period, time window. So now we get to the real problematic thing, which is, what about this? What about comparing the late switcher to the early switcher? Well, we know that we might think that like the first thing you're going to get is the average treatment effect on the treated for the late switcher, they're the treatment group, over its own post period, right? That's this little window right here, just like before. But unfortunately, we're subtracting the change in outcomes for the group K guys, okay? Now, the goal of subtracting their outcomes is that you're going to net out any differential trends or you're going to net out any common trends, you're going to net out any trends in untreated potential outcomes. But alas, when the when the control group is also treated, like it is here, group K has already been treated in the past, there might be another reason why their outcomes change over time. It might not just be untreated potential outcomes are changing. It might actually be that the treatment effect itself is changing. And so look in this red box, like the first piece is good. That's what we wanted, the ATT for group L over its post period window. But then actually, when you do the algebra down here, the bottom line is you're also subtracting out the change in treatment effects for group K, like for the control group. And this is like a real problem. It's a real problem when your control group also can have treatment effects. That's not usually what we think of as a control group. And like, that's not the point of even having a control group, right? We want the control group to show us a good counterfactual, what would have happened without treatment. But when the control group itself is treated, it's tough. You get in some problems. So to show you like why this is a problem, I'll give you a more provocative example. So imagine that we're here, and the treatment effects look like this. So all the pictures we were looking at before, the stylized stuff, if the treatment effect was just a shift, and that's good. Like that's the best situation for two-way fixed effects ever. But imagine that's not true, and the treatment effect's actually a trend break. So you should like go look at Scott Cunningham's Substack for today. It's about this paper by Jonathan Muir and Jeremy West about this exact issue in minimum wage studies, where they say, well, what if the minimum wage doesn't just shift employment? What if it just changes hiring patterns and employment changes, employment trends change? It's possible. There's like theoretical reasons that people have written down to think that that's how employment would change in response to minimum wages. So then you're in a picture like this. So, okay, what are we going to do here? Like, we can apply the diff and diff decomposition to a picture like this. And you can say, well, the first diff and diff is going to compare the early switcher, that's the dashed gray line, to the late switcher, that's the solid black line. And they're only going to do it, that 2x2 is only going to use data up until, but not including T star L. And that's fine. You're going to get a perfectly okay number when the control group is treated in the future, meaning it's not actually treated when it is serving as a control. Like that works. And you can see, like we can see here, the treatment effects are positive everywhere, right? It's a rising, it's a positive trend break. So the number you should get should absolutely be a positive number, right? The problem is this second diff and diff is in a case like this is very much not fine, because look at the outcomes that you're subtracting when you act like the gray line is a good counterfactual for the black line. These guys are going to be, the way I've drawn it and the way we've been making assumptions here, it's like their untreated potential outcomes are exactly the same. Like they're all on this flat trend. It's just going to continue forever, let's say. But because the gray line was treated and because the treatment effect is to shift its time trend, then we're going to think that a good counterfactual for the black line is that its outcomes changed a lot. If it hadn't been treated, the gray line is telling us like, oh, we think that outcomes would have changed like crazy for the black line. That's not true though. That's only because of the treatment effect. That doesn't say anything about what would have happened in the absence of treatment. And in fact, when you calculate a diff and diff in this picture right here, the black line falls farther below the gray line in the post period than in the pre-period. So that gives you a negative number. It's like not even just too small. It's that one is wrong signed, and you can get examples where the entire estimate's wrong. So you could run an event study and get like a positive trend break, and then you go to your computer to summarize that thing and make your tables, and you get a negative number, and you're like very confused. So this is the fundamental problem with two-way fixed effects. And I just want to say like I can show it to you in Stevenson and Wolfers. Like look at this event study. It's a trend break. It settles down after about 10 years, but it's changing. But if you were to average these post-period coefficients in the event study, it's like -5. But look at what the diff and diff is telling us. Look at the two-way fixed effects diff and diff. It's telling us -3. Like that's a very big difference. And especially when you get to the end of a paper and you've got a treatment effect, and maybe you're in a position where you're having to argue that your treatment effect magnitude is sensible, or maybe you're doing back of the envelopes with that treatment effect magnitude. If you're doing that stuff with a -3 and the real answer is -5, those are very, very, very different numbers. And so you could be way off if you don't get it right. You can see that this was going to happen if you go back to the decomposition. Like we said, it's not a problem to compare units to untreated units. That's okay, because untreated units are changing only because of counterfactual stuff. They're not treated. It's not a problem to compare units to future treated units because they're not treated yet. So their changes are counterfactual stuff. It is a problem to compare treated units to already treated units. So when you look here at the later treated group versus earlier treatment group, the average diff and diff among those dots is like a positive 3.5. Whereas among all the other dots, basically it's a negative number, sometimes a pretty big negative number. And so you can already see like this decomposition plot is like screaming at you. The bad ones are all here. Like they're all, the problematic ones are all right there. And that's very typical of like where the problems should come from. And I just want to say too, like once you sort of see that this is how two-way fixed effects works, you can't unsee it. Like you'll see it everywhere. So this is a paper, this is like a really good paper by Richard Baker about what happened to children's educational outcomes when the boll weevil spread through Georgia and ate up all the cotton bolls. So this is just the first stage, bales of cotton gin. The boll weevil is obviously pretty bad for cotton production. But you look at this event study right here and you say, oh, well, look at that. Like the average event study coefficient, these are big numbers. It should be something like a 42% reduction in cotton production if you eyeball it from that. The diff and diff coefficient in the paper is negative 20. It's like half as large as it should be. Here's one about the introduction of Uber into a city and ambulance volume, which is where the story is, if you're hurt and it's not that serious and you don't want to get nailed with an ambulance bill, you just call an Uber to go to the hospital. And if you sort of eyeball a diff and diff coefficient here, whatever this ambulance rate, whatever these units are, this is like -5 maybe effect on ambulance utilization. The diff and diff in the paper is -1.5. So it's just way too small. So these can be a real problem. And I think two-way fixed effects as a summary measure, when you just put in one coefficient on the right-hand side, can really give you a number that's misleading. And specifically, it's typically going to be misleading in that it's biased away from the sign of the true treatment effect. You could have all sorts of weird treatment effect dynamics that screw that up. But if it's like a trend break that goes negative, your diff and diff is going to be go towards 0 and maybe become positive. If it's a trend break that's positive, your two-way fixed effects is going to be close to 0 and maybe go negative. So I think that probably like the last thing that I'll say is that there's one like link in the chain here that's kind of missing and that I don't address in my work, which is I'm showing you, for example, event studies, and I'm kind of implying that the event studies are giving us the right answer, and then two-way fixed effects like diff and diff with one coefficient is giving us a biased answer. So you might say, oh, well, is event study okay? Why don't I just do an event study? Alas, Sun and Abraham, which is also out, I think, in the Journal of Econometrics, they show us that that's unfortunately not generally true. I would say event study estimates where you have two-way fixed effects, but you put dummies in for many dummies for periods before and after treatment, they're better, but they're not perfect. So basically, Sun and Abraham take the more theoretical approach. They assume parallel trends in counterfactual outcomes, and then they say, how should we interpret a given event study coefficient, right? And sadly, their conclusion is that it's not always going to work out very well. Each event study coefficient is an average of treatment effects at all other event times. And that's just kind of a scary result. I should say, like, the time that Sun and Abraham tell us that is okay is when every treatment cohort has the same shape. If the trend break is like the same for everybody, event study is great. I don't think any of us are going to convince referees that that's true. So sometimes it's going to work fine. I think there's people who are like, you should never ever do two-way fixed effects, and I might never do two-way fixed effects again. But I'm not saying it's necessarily wrong. But Sun and Abraham show that, like, if different units have a different shape of treatment effect path afterwards, like somebody has a shallow trend break and somebody else has like a really steep one, or somebody like reverts and somebody else like stabilizes at a low level, like any way that the shape is different, that's going to bias every single event study coefficient. So for example, you could run an event study and get weird garbage looking pre-trends and be very disappointed. But actually then the Sun and Abraham result is on your side, and they say, no, you don't have to trust those. Those coefficients might not be reliable. Instead, what you should do is use some of these other new kind of methods. So like, maybe Richard Baker in 2015 was worried about this little pre-trend in the bales of cotton ginned first stage, but perhaps he shouldn't have been, because Sun and Abraham tell us each one of these dots is an average of like all the other treatment effect parameters. So unfortunately, I'd say, unfortunately, the message is two-way fixed effects event studies not always okay. But the upside of that message is if you've ever gotten a kind of weird, fishy looking event study, it might actually be fine. And in some other ways, like the real upshot of all this, I'm telling you all the reasons why a single diff and diff coefficient in two-way fixed effects is not that great. Sun and Abraham are telling you, you probably can't really solve all the problems by just being more flexible about your specification. But actually, like there are solutions out there. And when you use stuff like stacked diff and diff or Callaway and Santana, you address none of these things are problems. And the answer you get is good. Like if you have a messed up pre-trend, you really do have a messed up pre-trend. If you have a nice flat pre-trend, it's good. And no econometrician is going to come take it from you. So that's all I'm going to say today. There's more in the paper using, like some of my favorite stuff in the paper is about using the decomposition to compare two specifications and say, I used weights or I added controls or I like put in some other kind of fixed effects, like why did my number change? I think there's a lot of cool stuff about that. But that used to be my focus when I first wrote the paper, and I was holding out more hope for two-way fixed effects than I still do. Now I would tend to get to this point in the analysis and say, you should do something, you should try some other estimator, and it'll work out better, and it'll put you on firmer footing and give you an answer that you're more likely to be able to trust. So I'm going to stop there, and I'm happy to keep on like answering questions about any of that other stuff.
Awesome, thanks very much, Regan. I think that we will open up for like a few questions. I don't know if you can see the raised hands in the chat, and you can just call them out, and then maybe we'll do, I don't know how much time you have for questions, so maybe we'll do like 10-15 minutes. Does that sound reasonable for you? Because we still want to do the afterwards. You still have some software stuff that we wanted to get to afterwards. Cool. Where we actually are going to go through some of these examples with the Bacon decomp, either in R or Stata. So I think that's the plan, but we'll see how many questions there are and everything. So we'll keep it cool.
Yeah, that sounds great. Okay, Claire, let's see.
Hi.
Hi.
Thanks for the talk. It was really super clear and really helped me to understand the paper.
Good.
I have a practical question about how you would go about starting a multi-time period diff and diff analysis. Like, would you still start with two-way fixed effects, check the Bacon decomp, think about late adopters, and then sort of know that your effects are biased towards zero, and then move to another estimator?
Yeah, I probably start that way now still. I don't know if I will do that forever though.
Right.
Because I'm not like an R person. I'm very happy to see some of these new like Stata packages that people are writing that call the R program. I have some like really messy code to do like stacked diff and diff, which is, I didn't talk too much about it, but it's basically just like where you physically take one treatment group and you match it up to a set of controls you know are good. And then you do that again and again and again for every group. And then you know exactly what you really are controlling, what comparisons you make. Yeah. So I have a paper like that where so I probably would have started with two-way fixed effects before and checked the Bacon decomp and then been like, do I need to do these other methods? But I guess my thought process on this has turned into something more like this. Okay, so suppose I do two-way fixed effects and I find and then I compare it to like a Callaway and Santana or a stacked diff and diff or a new estimator, and it's the same.
Yeah.
I don't know, why not use the new, if it's the same, it doesn't matter. So why not use the new estimator? And if I find out that it's different, then I have lots of reasons in my head now to prefer the new thing instead. And so I'm pretty sure that I'm like moving way towards just doing newer estimators, because I really do think I understand what they mean like quite a bit more. So I guess I can be even slightly more clear about that. Like if you go back to a scatter plot, like the decomposition, like any of the new methods, like the estimator and Deschies-Martin and Divoree, Borusiak and Jaravel, Stresnev, Callaway and Santana, Sun and Abraham's estimator, like there's all of them. They're all doing some version of just getting rid of this bad stuff.
Yeah.
It's all kind of the same. It's not exactly the same, but it's kind of the same. And they're giving you different control over like, how do you want to weight these dots together? You know, do you want it to kind of happen automatically, or do you want to choose that at the beginning? And there's lots of little details that are consequential, but basically they're all doing some version of this. And yeah. I think it's good. I think this decomposition is a true fact about two-way fixed effects, but it's complicated, right? These new estimators in some ways are a little harder to do, but the answer you get is way clearer it's much more straightforward to keep in mind.
Yeah, something I've run into is that the Callaway and Santana and also your package are relatively slow with big data. And so I think something that I've learned is at least just starting with two-way fixed effects and then moving forward when you have your specification, I think can be helpful. So that was
the only thing I would say about like large data sets and things moving slowly is that I'm also a huge fan of like just collapsing data. So everything in here could have started, you could have started with units, like units I, that could have been a billion Austrian workers in some awesome administrative data set. But if the treatment is like the firm at the firm outcomes or something, you could collapse to the firm. And actually you can go even farther and you can collapse everything down to just like averages for people who are treated at one time. That can just be one average. So there's collapsing ways, I think, the way I think about it is like the regression is basically functionally collapsing anyway. So you can collapse and just save yourself a bunch of time.
Thanks.
Yeah, Jacopo.
Sorry. Thanks for this. This was very helpful. My question is regarding reversible treatments, which is not really a staggered design where, you know, the policy goes from 0 to 1 and that's it.
Yeah.
But what if the policy then can go from 1 to 0? And I have to admit that I've been reading a bit, and I think you touched on that in the appendix.
Yeah.
But I want to hear.
I just like barely touched on it. No, it's true. That's a good point. I mean, I put like one tiny thing in the appendix about it because the point there was to say, suppose you had one unit that turns on and then it turns off, and then you have a comparison, you have a control unit that just never turns on at all. You can, that actually, to the two-way fixed effects version of that works just like the timing, the two group timing thing that I showed. Like there's going to be the turn on estimator that's like compare the unit that switches on to the unit that stays constant up until the switch off time. That's one piece. And then the flip side is compare the unit that switches compare the switching off time, like starting when it's on, before and after it turns off, and then again. So it kind of, it's a weighted average. It's a lot like it. My one sort of mechanical comment is you could just power through this kind of derivation with units that turn off and it would work. It would just be like a lot more complicated, but that's possible. That's doable. The only other thing econometrically that I think is worth thinking about with treatments turning off is that then you have to worry when you define the treatment effect you get for the turning off, you have to think about whether or not there's persistence in having been treated. And so that just is a little trickier. And it's interesting. I've seen papers that do it, and I've talked to people who get a lot of mileage out of trying to explicitly separate what are the estimates of the turning on and what are the estimates of turning off. And often if like the thing is persistent, you get like a bigger number for turning on than turning off, because if you have a program and it's still doing good stuff, even though it technically goes away, the outcomes don't really revert quite so quickly as maybe they jumped up. That's not always true, but it can be true. So yeah, it's a little bit of a trickier situation, but I don't think it's really fundamentally different, except in that treatment effect dynamics matter for the interpretation in potentially a new or nuanced kind of way. Oh, Mark.
Hey, I had a question, like how these like results of the decomposition would work on when like same unit is treated like or can be treated multiple times. So let's say like new teachers arriving to a class that you could get like, or the same grade could get like a new teacher every 2 years or something like that.
Yeah. Yes. Okay. That one, to me, that one's just like the Wild West here. It's like, it's total, people, it happens all the time. Again, this is the thing I've learned from just getting like drawn into these discussions with proper econometricians, is the way they would say that is the space of potential outcomes just starts to like multiply like crazy, because now the potential outcome here is like treated at which time, and you could, a given unit potentially, right, could be treated at any different time. And we can imagine a full space of potential outcomes being treated in 1971, but what if Alabama had instead been treated in 1977, or instead, if you have two treatments, then you've got that full space of like, when were you first treated? And then you've got this, it's now a combo of like, when was your first treatment? And then when was your second treatment? Like if you got treated in 1 year, it's a different potential outcome to get treated 2 years later than it is to get treated 7 years later. And so it's not impossible, but the part of the reason it's so hard to compare is, or so hard to develop estimators, is that if you want to compare units who are like real, I don't know, it's just, it's tricky. And the space of treatment effects that you have to consider when you're trying to understand, like, how do I interpret this? It really can get cumbersome. So I would say that probably the way that people would try to tackle that now on the theory side would be to say something like, well, we're going to have to consider restrictions on the treatment effects, like, the treatment effect fades after 5 years, or treatment, something like that. Then it would make the interpretation a little bit easier. Practically speaking, people will do a couple of things that might work. Okay. One that I have kind of used in the past is to treat the first event just kind of like the only event. So in my paper on community health centers, our treatment was not getting any health center grant, which happened many times. Counties got refunding lots of times. Our treatment was, when did you first get funded? So it was like health center establishment. And then it was like, that was the treatment. And then we used subsequent funding as kind of like an endogenous variable. So we could put a dummy for like, did you get a grant in this year? And that was one, like, all the time. We could put it on the left-hand side and do event studies around the event called first health center grant. That's one way. So that's kind of just that's taking a more complex thing and just like boiling it down to a simpler thing, which in some cases that's a sensible approach. Like I think it made logical sense in the context of grants. But in other examples, it doesn't make any sense to do it that way. Sometimes people will take a unit that's treated multiple times and they'll repeat it in their data set, and they'll only code up dummies for like one of the treatments for each time that unit is repeated. So Julian Lafortune and Jesse Rothstein and Diane Johnsonbach have papers on school finance regulation, school finance reforms. And a given district might get hit with a couple of different reforms. And so if your district is hit twice, they're going to repeat your observation. And in the first one, they're going to code up dummies around your first treatment. And in the second one, they're going to code up dummies around your second treatment. Then there's a paper by Ryan and Danny Sandler that I think concludes that actually is not a good idea through some simulations, but they say the other alternative is to code up several different sets of variables, which is like, here's a dummy in my data set that equals, do you have your first treatment? And that's it. And then here's just another dummy on the right-hand side that says, do you have your second treatment? And here's another dummy that says, do you have your third treatment? And they're just all on the right-hand side together. So those last 2 or 3 things are all just different two-way fixed effects specification choices that could technically handle this case, but none of them really address, like, on a deep level whether it works or not. And so I guess that is a long way to say we don't totally know what's the right approach for that, because the rigorous econometrician answer gets wildly complicated, and then the practical applied person answers sort of kind of, maybe they seem like they work. They don't seem to be spitting out like meaningless stuff, but it's a little hard to know how to interpret them all the time.
Thanks.
Mm-hmm. Sorry, I don't know if anybody, I assume that raised hands jump to the top.
I do not have another question. I just wanted
Okay.
to ask whether you have the references for the papers that turn off. I think someone has asked it in the chat.
Oh, yeah. Let me look back. I'll share them with Taylor if that's all right. I need to look back. I remember going to a couple of seminars and asking people about this. I think they were like environmental papers.
Thank you.
Okay, Eski.
Hi, hello.
Hi.
Thank you for the great talk. I have a practical question too, and it's related to the software packages actually, a little bit. So now I'm working on a staggered diff and diff, and I wanted to use the Bacon decomposition, but I'm using, so my unit is municipalities, and I'm using state by year fixed effects. So I want to compare to the same municipalities in the same state. So I talked to the guys who wrote up the R package to see whether this is doable within their package, and they said no. And I was wondering if it's I mean, to me, it seems doable theoretically, but I wanted to check with you.
Yeah, no, it's doable. Okay, so I should say, like, I really like state by year fixed effects or region by year fixed effects because I know what they do, which is usually not actually true for like other X's you might want to throw on the right-hand side of a regression. But I mean, I think that one would say, I think if you wanted to accommodate that kind of specification into like a Callaway and Santana thing, all you're really saying is that you would like to take municipalities treated in, I don't know, 2001 in Florida and compare them to a clean control group of other municipalities in Florida. And that's like that would be like one ATT GT or something. And then you want to do the same thing in Kansas and the same thing in Washington and the same thing in Texas. I'm sure you could kind of back that out of the Callaway and Santana estimator by doing things like feeding it data from each state like one at a time, and then taking the ATT-GT estimates from it, and then you could aggregate. Now, of course, you're not going to get like nice bootstrap confidence intervals from doing something like that. But if you said, oh, I did Callaway and Santana 50 times, and I got ATT-GT estimates for each state on its own, and then I aggregated those together, you could do that. You could, and that would be just like, actually, in some ways, that would be great. That would be better than saying the thing that we all say, what I've said in papers, like we include state by year fixed effects. That would be much more explicit about what state by year fixed effects actually even do, which is saying, I do a Callaway and Santana estimator, and I only include controls from the same state. It's kind of, and that's what state by year fixed effects are doing anyway, but you would then wind up being like way more explicit about it. So I think it's worth, I guess that's sort of a half answer. Like, I think I can tell you how I would go about trying to get the point estimates for something like that, but I don't have anything good to say about how you're going to get bootstrap confidence intervals for that particular kind of specification. Nicole.
Hi, yeah. I have a quick kind of back to the theoretical side of things question. I understand the weights are kind of a combination of the sample sizes and variances, but can you speak a bit more to how negative weights can arise?
Yes. Oh, that's really important. Okay. Yes. Good idea. There are two different kinds of weights that are getting thrown around out there in the world with this literature. Okay. They're like my weights, the weights I talked about today, are always positive because they're sample size and variance, right? Neither of those things can ever be a negative number. And the key thing, the reason that that's true is because those are weights in the estimator, right? They're not weights on treatment effects. They're weights on like 2x2 different ifs. They're weights on Y bars. They are sample things, okay? So this is really a key distinction. And I think people are confused. Like I've seen people who've gotten comments or something like that, or people have asked me like, oh, well, how can I evaluate whether I get negative weights in your decomposition? And you cannot, there are no negative weights in my decomposition. The reason negative weights arise, we kind of saw it, but we maybe like zipped through it a little bit, the reason negative weights arise is that when you have something like this and you move to a theoretical interpretation, right? So what I'm telling you with the positive weights is that on this term right here, beta hat dd comma L sub KL, like that is just a function of y bars in the data, and this will always be weighted positively. But then when you ask yourself, what is the interpretation of this number? What I'm showing you in the red box is that it is a treatment effect for the treatment group L minus the change in treatment effects for the control group. And here you see this minus attached to ATTs. This is where negative weights arise. So negative weights arise in the way that you interpret the treatment effect of a given 2x2 estimator. So the estimators are always weighted positively together, but some of the estimators are themselves like differences in treatment effects. And so the negative weights come through the interpret. That's why the negative weights, they only exist in theory. Positive weights are on your data, like it's always positive weights. It's just in theory, there are negative weights attached to treatment effect, like theoretical parameters. Does that make sense?
Yeah, that does. Thank you a lot.
Okay, yeah, it's really confusing. And so it's like, that's what people say there's a negative weighting problem. There is, but it's not in the way that OLS handles the data. It's in the way that you interpret a given 2x2 or a set of 2x2s.
Awesome. So I think that we'll wrap things up there. So thank you very much, Bacon, for the great presentation of this paper.
My pleasure.
It's a great introduction to this literature for the reading group that's just getting started. So
cool. Let anybody feel free to reach out with questions. I have like a couple of emails that I've been meaning to respond to on this. I try to respond to people's emails. So let me know if you have questions about this. And I have trouble convincing people sometimes that I really do like talking about diff and diff a lot.
Awesome. So
thanks.
For anybody else who wants to stick around, we're going to maybe do some coding up. There are some examples with the software packages. We can split into Stata and R segments if we want to do that. But if I know it's at this point, it's been just about an hour and a half since this was supposed to start. So if you have to jet, no worries.